All right, good afternoon, good morning, good evening, good night, depending on when you're watching this video. In this illustration, I'm going to be working through and discussing the simulator that's given on the link provided at the end of slide number 29. So if you follow that link, you'll come to this stats interactive page titled the central limit theorem. So what I'm going to do is use this simulator to explain how the central limit theorem works, and hopefully give you a little bit more insight into what the central limit theorem presents to us in terms of non-normally distributed populations. Right. So let's start at the beginning. We have to pick a seed. This doesn't really matter. I'll use seed 6953, random number. You can use the same one to replicate the same results, or you can pick your own seed. It doesn't matter. The overall theme and the overall result will be the same. Okay, let's start with a normally distributed population. We select the mean of the population. It doesn't matter what we pick. The results still are going to be the same, with the only difference that the sampling distribution parameters will be different depending on the values of the mean and the standard deviation we pick. But the overall shapes of the distributions will be similar regardless of these values. So let's say that our population has a mean of 1 and a standard deviation of 2. Generate population. So this blue histogram here represents our normally distributed population of interest. And you can see that this histogram looks very normal, symmetric bell curve, centered at 1. And the spread of this histogram would represent a standard deviation sigma of 2. Okay, let's suppose that we collect samples of, well, let's start at the beginning, or let's say we collect samples of size 5 from this population. All right, and let's, just for illustrative purpose, okay, well, we can't do 1. So we'll collect samples of size 5, and let's say we collect 50 samples. So 50 different samples of size 5 are being collected. Sample. All right, so this value here represents the mean of sample 1. So we collected 1 sample of size 5. We wrote down our 5 values. We calculated the mean, and here's the sample mean. Okay, now we collect the second one. So here's the mean of sample 2. Here's the mean of sample 3, the mean of sample 4, the mean of sample 5, the mean of sample 6, sample 7, etc. So we can just keep adding the different means to the plot. So for every sample that we collected of size 5, we've computed the mean, and this bottom plot is representing the value of that mean. Okay, so as we build this up and we get to the end of our 50 samples, we have a shape that sort of looks like this. And what this is starting to take on is the shape of a normal distribution, because our population is normally distributed. All right, let's say that we collected 150 samples. The result is going to be the same. So as we continue to add points to the graph here, so each of these are sample means for samples of size 5. We continue to add points, we continue to add points, we get up to our 150th sample. You can see that this thing looks even more normal than the original illustration, or the first illustration where I only had 50 samples. Okay, let's say that we collect 500 samples now, plot this. Now you can really start to see that normal shape coming into play. And this is what we would expect, because if our population is normally distributed, then the distribution of the sample mean is also normal. This is a fact, and we can utilize this, and we have utilized this in previous exercises. Okay, what does the central limit theorem say to us? Well, let's say that our population is not normal. So we can choose skew right or skew left. I'll do skew left. Same mean, same standard deviation. So this is now the generating population. Okay, let's say that we collect a sample of size 5, and we'll do 500 samples again. So this is the exact same idea. We've collected a sample of size 5 from this skewed left population. We've computed the sample mean, and we've done this 500 times. Then we just start to mark them down. Okay, so what do you notice? Well, this is slightly more symmetric than the original population, even for only samples of size 5, but it's still left skewed compared to a symmetric bell curve. All right. So the central limit theorem tells us that when n is greater than 30, the distribution of the sample mean should be approximately normal. So let's say that we move up to 25. What we're going to expect here is a sampling distribution that's still slightly left skewed, but closer to normal than the original illustration. Because as we close in on that sample size requirement of greater than 30, the distribution of the sample mean becomes more and more normal. So if we mark down these points, we have something that looks like this, and you can see it's still slightly left skewed, but it's far more normal than the original simulation that we had before. Okay, let's say we go up to 50 now. We collect 500 samples. This is quite a bit more symmetric than the original illustration. Okay, let's up to 1,000 samples now. And you can see that this here for samples of size 50 looks quite symmetric compared to the previous two illustrations preceding the last one. Now this is quite thin because the standard deviation is quite low, so the values are clustering tight to the mean. So let's go back to our generating population. Let's up the standard deviation to 4. So we have something that looks like this. Let's collect samples of size 50 again. We'll do this 1,000 times. Okay, we've marked down our plots, and now you can see again this quite normal shape. If we up to 100 samples, we do this 1,000 times, we mark them all down, this looks very normal. So the point is, what this simulator is showing us is that when we sample from skewed distributions, and you can replicate this using right skew or left skew, as your sample size increases, the distribution of the sample mean, which is this down here, becomes more and more normal. So when we collect samples of size 100 1,000 times, and we mark down the mean of those 100 values, we have something that looks very normal, even though the generating population is left skewed. But when our sample size was less than 30, so say 5, and we repeat this 1,000 times, we end up with something that still looks left skewed because, again, the central limit theorem says we need at least 30 observations in order for this distribution to be approximately normal. So I encourage you to play around with this. Try generating from different types of distributions, skew right or skew left, change the parameters, but every time you increase the sample size, you'll end up with the same result regardless of the generative population, so regardless of the population shape, which is a sampling distribution that is approximately normal. And that's what the central limit theorem is stating. All right, so as always, if you have any questions, please let me know.